Now, if the positive integers, suppose a and b are any two positive integers, a and b fall in surplus, then has the factorization, a and b have the factorization, a equals product I ranges from 1 to infinity, pi power ai, and b equals product I ranges from 1 to infinity, pi power ba. Then consider the GCD. Then the GCD of a and b has the factorization product I ranges from 1 to infinity pi power ci, where ci is minimum of ai/b. ci equals minimum of ai/b. So this is an important result. If a and b are positive integers and a and b have this type of factorization, means a is product I ranges from 1 to infinity pi power a, and b equals product I ranges from 1 to infinity pi power bi, then their GCD, the greatest common divisor of this a and b, has a factorization product I ranges from 1 to infinity pi power ci. What is ci? ci is mentioned in this way. ci is minimum of this powers of this exponents a and a and b. How to prove this one? So for let d equals, let d be the GCD of a and b. Let d be the GCD of a and b. That means d equals product I ranges from 1 to infinity pi power c. Okay. So let d equals this product I ranges from 1 to infinity pi power ci, where ci is mentioned here, such as minimum of a, the exponents a and b. So what is ci? By the choice of the ci less than or equals a. Okay, ci less than or equals this a. ci less than or equals a means for any prime pi, so pi power ci less than or equals pi power a. Clear? That means this product I ranges from 1 to infinity pi power ai should less than or equals, pi power ci less than or equals product I ranges from 1 to infinity pi power a. What is this one? Product I ranges from 1 to infinity pi power ci. There is a d. That means d less than or equals. What about this term? That is a. D less than or equals a. D less than or equals a means this d must divide a here. Okay. Similarly, by the choice of ci, we have ci less than or equals bi. Then product pi power ci less than or equals pi power bi. Again the product less than or equals that one. So finally it is d less than or equals b. That should imply d less divides b. That means d divides a and d divides b. That means d be the common divisor of a and b. So here we got d be the common divisor of a and b. But our requirement is to show that d is a greatest common divisor. So how? If possible, e be a common divisor of both of this a and b. Let e be a common divisor of both a and b, and we write that e be the common divisor of a and b, and we write e equals product I ranges from 1 to infinity pi power ei. Then surely pi power ei. Then we have this ei less than or equals ai and this ei less than or equals bi according to this argument. Why? Because this ei can be chosen as minimum of a and b. Why? Because our requirement is d. Here we obtained d as a common divisor, but we have to show that this d is the greatest common divisor. So for every since d is a common divisor, then if e is another divisor of this a and b, then that e also this divides d. Then we say that this d is a greatest common divisor. That is by the definition of this GCD. Okay. So for that, let e be the common divisor of both a and b. If a and b has another common divisor, that common divisor should divide d then D is the greatest common divisor. Let E be the common divisor of A and B. Then the common divisor of A and B can be expressed as in this way. So that E equals product I ranges from 1 to infinity Pi power some Ei, where this Ei is chosen as minimum of A and B. So according to these arguments, by the choice of this Ei less than or equals Ai and Ei less than or equals Bi. Surely product Pi power Ei, this implies Pi power Ei less than or equals Pi power Ai. Then this product less than or equals 31, that means E less than or equals A. Similarly, we can show that E less than or equals B. Therefore, E less than or equals A means this A divides E and E divides A and E divides B. E divides A and E divides B means surely this E divides D. So this common divisor D is nothing but a greatest common divisor. Why? Because D is a common divisor of A and B. If we choose another common divisor of E, then we say that this E divides this D. Therefore, D is a common divisor. So this is our proof. That is, if A and B, any two positive integers has a representation, the product I ranges from 1 to infinity Pi power Ai and Pi power Bi, then their greatest common divisor has also is of the form D equals Pi power product I ranges from 1 to infinity Pi power Ci, where Ci is chosen as minimum of A and B. Okay. Now we have an important result. That means, here let us discuss about the series of reciprocal of primes. Series of reciprocal of prime means consider an infinite series. An infinite series sigma 1 by p power m. Infinite series sigma 1 by p power n, where n ranges from where to where? N ranges from 1 to infinity. This is an infinite sum of reciprocal of the primes. Sigma n ranges from 1 to infinity, 1 by p power n, then our requirement is this 1 by p power n always diverges for n greater than 1. How to prove? So this is an important result, but this is a familiar result, 1 by p raised to m or 1 by a raised to m, that always diverges when m greater than 1 and so on. We already proved it in real analysis. But we have, when p is a prime, 1 by p power n diverges. How to prove this one? So the proof is done by contradiction method. Let sigma n ranges from 1 to infinity 1 by p power n converges. Suppose it is p power n converges. 1 by p power n converges. Since it converges, we know that there exists an integer k following such that sigma k ranges from or m ranges from k plus 1 to infinity, m ranges from this k plus 1 to infinity 1 by p power m, it is strictly less than 1 by 2. Okay. Here our requirement is sigma 1 by p power n diverges, but we assume that 1 by p power n converges. Since p be a prime, the least prime is 2. So clearly since it is converges, there exists a integer k such that sigma m ranges from k plus 1 to infinity 1 by p power m should less than 1 by 2. Sure, why? Because p is the least prime, p is 2 here, so that inequality should hold. Okay. Now, let's consider Q. Q equals P1, P2, etc. into some Pk. Then consider the number 1 plus nq. Consider 1 plus nq, where n equals 1, 2, 3, etc. Q, what is Q? Q is P1, P2, etc. Pk, product of primes. Q may be composite. Then consider this 1 plus nq, where n is 1, 2, 3, etc. Now, clearly this Pi doesn't divide this 1 plus n. None of the numbers is divisible by any of the primes P1, etc. Pk. Why? Listen, Q is the product of these primes, and 1 plus NQ, where N is natural numbers, N foreign set, so N is a natural number. Clearly this Pi, none of this number P1, P2, etc. P2. Now none of this number 1 plus NQ, none of this number is divided by, none of this number 1 plus NQ is divided by any of the primes P1, etc. Pk. That's a crucial. Why? Because of choice of this one. Okay. None of this number 1 plus NQ divided by any of the primes P1, P2, etc. Pk. For example, suppose P1 equals 3. P1 equals 3. That is a first order prime. P1 equals 3. Then N equals 2 or N equals 1. So it is 1 plus NQ become N equals 1. 1 plus NQ become 1 plus 3. That is 4. So this means 3 does not divide 4. If you choose any PIs, any product, or P1 equals 3, P2 equals 5, next prime, N equals 2. What happens here? 1 plus NQ. Q is 3 into 5, 15. NQ is 2 into 50, 30. 30 and 1 plus 31. So this 31. There is 31. So 3 doesn't divide 31 and 5 doesn't divide 31. So if you choose Q and the number is of the form 1 plus NQ, then clearly we can say that no number 1 plus NQ can be divided by any of the factors or any of these primes P1, etc. Pk. Means Pi doesn't divide 1 plus NQ where I ranges from 1 to K. Okay. Now, therefore, all prime factors of this 1 plus NQ, what is 1 plus NQ? NQ is Q is a composite number. Why? Because it is the product of primes. N is any natural number. So 1 plus NQ may be either prime or composite. So this 1 plus NQ can have a, but we know that the 1 plus NQ, every composite number can be expressed as the product of primes. So 1 plus NQ has a prime factorization. Let 1 plus NQ or the prime factors of this 1 plus NQ that occur among the primes Pk plus 1 into Pk plus 2 or P among the numbers Pk plus 1, Pk plus 2, etc. 1 plus NQ is maybe it may be composite, then it has a prime factorization, but Pi doesn't divide 1 plus NQ for I ranges from 1 to NQ, therefore 1 to K. Therefore, all the prime factors of this 1 plus NQ occur among the primes Pk plus 1, Pk plus 2, etc. Therefore, for each r greater than or equals 1, then sigma n ranges from 1 to r, 1 by 1 plus NQ, 1 by 1 plus NQ, which is less than or equals sigma t ranges from 1 to infinity, sigma m ranges from k plus 1 to infinity, 1 by p power m all power p. Why? Because what is 1 plus NQ? Because we have 1 plus NQ. 1 plus NQ, since 1 plus NQ greater than or equals p power m. Okay, 1 plus NQ, because 1 Pi doesn't divide 1 plus NQ for I ranges from 1 to K. Therefore, this 1 plus NQ always greater than or equals p power m. Why? Because it has a prime factorization, or the prime factors of 1 plus NQ occurs among the primes Pk plus 1, Pk plus 2, etc. Therefore, 1 plus NQ greater than or equals p power m. Agreed. So, 1 plus NQ greater than or equals p power m for some m greater than or equals k plus 1. Agreed. Therefore, 1 by 1 plus NQ less than or equals 1 by p power m. Thus, sigma n ranges from 1 to r, 1 by 1 plus NQ less than or equals this summation. Okay, that means, so which is less than or equals sigma t ranges from 1 to infinity. What about 1 by p power m? Strictly less than 1 by 2, so it is 1 by 2 all power t. So come to this right side. Sigma t ranges from 1 to infinity, 1 by 2 all power t is nothing but a geometric series having common ratio 1 by 2 less than 1, therefore it should be convergence. then sigma n ranges from 1 to r, 1 by 1 plus nq has a partial sum. It is a partial sum, therefore it is bounded, hence it is bounded partial sum, hence it is convergent. Okay, it should be converged. Now, let xn, consider xn equals 1 by n and yn equals 1 by 1 plus n. Here we know that, or here we obtain this series sigma n ranges from 1 to r, 1 by 1 plus nq has a partial sum, bounded partial sum, hence we know that, hence it is convergent. But we choose the sequences. Let xn equals 1 by n and yn equals 1 by 1 plus nq. Okay, take r. Choose r such that let r equals limit n tends to infinity, limit n tends to infinity xn by y. Let r equals limit n tends to infinity xn by yn. That means r equals limit n tends to infinity. What is xn? 1 by n by 1 plus nq. Okay, yn is xn is 1 by n, yn is 1 by 1 plus nq. 1 by 1 plus nq. So that equals 1 plus nq by n equals 1 plus, yes, 1 plus nq by n. So it is that is limit n tends to infinity, which is equals limit n tends to, then limit n tends to infinity 1 by n by 1 plus, sorry, 1 by 1 plus nq, that is limit n tends to infinity 1 plus nq by n. So which is equals, it is, that equals limit n tends to infinity n into 1 by n plus q by n equals q itself. Okay, so here r equals limit n tends to infinity of xn by yn, but it is q, then this q differs from 0. Why? Because q equals the product of primes, then each pi's are non-zeros, therefore this q strictly differs from 0. Then means r is the sigma, sorry, limit n tends to infinity xn by yn, that is q, which is non-zero. Then we have here, we know that by the comparison test, when sigma xn converges, if sigma yn converges, then we have, since sigma xn converges, if sigma yn converges by comparison test. But we know that here sigma yn, what is sigma yn? Sigma yn equals sigma 1 by 1 plus nq. So here we know that sigma 1 by 1 plus nq converges. Therefore, by comparison test, sigma 1 by n converges. That's a contradiction, because we know that sigma 1 by n always diverges. This contradiction is due to our wrong assumption. Therefore, sigma 1 by p raised to n always diverges. So that is the result.